I grew up in a mathematics household. My father was the vice president of the AMS 60 years ago, and this is actually the first math conference that I've been in. Although my degree is in theoretical physics, and I've been a theoretical physicist, and I've been doing mathematics most of the time. But, you know, 100 years ago, every mathematician, or almost every mathematician, was also a physicist. And I'm going to have some comments about that. Historically, this map outlines the history of geometric algebra and calculus. The key ones that I want to mention are Hamilton's Quaternions, because that's this group, and then Grossman's algebra. Now it's kind of ironic that Hamilton and Grossman understood, they were contemporaries of one another, and they tried very hard to understand one another, but they couldn't. Now they had different languages, but both Hamilton and Grossman were linguists. And the fact that they were not able to understand one another is quite remarkable. But William Kingdom Clifford came to the rescue and put them together and found out how the ideas in Grossman can be integrated with Quaternions. That then became what is known as Clifford algebra for the next century, and it was just regarded as one more algebra among many other algebras. But in fact, I would argue that in fact it's a universal algebra, and I'll give you some points to help support that. I got the connection with Clifford algebra from ideas of mathematician Marcel Rees in 1958 in an obscure publication, which probably would have been obscure, continued to be obscure, except I advertised it, and it was the foundation for a book, Space-Time Algebra, published in 1966, which puts together the historical trends both in physics and mathematics. So there has been a there's an international community of people working on geometric algebra and calculus, and it is now a comprehensive mathematical system that has been applied and developed in physics in all branches of physics and in all domains. And it even has considerable applications for high school mathematics as well. So we could spend a whole hour on any one of these little boxes, but I just wanted to give you an idea. I claim, and I believe others will agree, that this is the mathematical system that has a wider range of applications to all of physics and maybe all of mathematics. Mathematicians have other ideas. Okay, let me just talk about some of the intuitive ideas. First of all, we want to do a correspondence between geometry and algebra. As you know, the interplay between algebra and geometry has been a major theme in the history of mathematics from the beginning. So let's do the following comparison between geometric objects and algebraic objects. By the way, I want to apologize. You may not know this, but I was to give this talk 1 year ago in San Diego, but then I had a stroke. And consequently, I still have some of the vestiges of the stroke. And the consequences are that I have difficult connecting my output from my ideas or my understanding. It's actually a problem of the coordination of left and right brain, because the stroke was on my left brain, and the right brain, which is the geometry part, that works just fine. So I have some trouble finding smooth turns sometimes. Okay, so we draw the following correspondence between geometric objects and algebraic objects. You're very familiar, of course, with the concept of a scalar and a vector as a directed line segment. But now we can have, vectors have different directions. And so a natural definition, you'll notice that the two arrows, A and B, when they are end to end, they determine a circulation on the area of the area. And then we have the product of three can give us a volume element, which is a volume element in 3 dimensions. This is not the way that Grossman said it, but this is Grossman's idea. Okay. Now, an interesting thing about the orientation, notice if we put the arrows along the order in a different order, we get 2 oriented areas, which are defined by the antisymmetric product. And then this is another aspect of that vector, and that's called a bivector. Now, geometric algebra, Clifford, by the way, is all honor to Clifford for Clifford algebra, but Clifford himself wanted to call it geometric algebra. And I think that is correct, and I think that it actually is a major theme in the history of mathematics, including its applications for some time. Okay, so now you are familiar with the interpretation of an inner product as a projection from one vector on another. And then the antisymmetric part, notice the inner product, scalar value, is symmetric. The outer product is skew symmetric, and the meaning of the skew symmetry is that there's an orientation in a two-dimensional object. They can be combined, and this is the remarkable thing this is the essence of Clifford's contribution. That the product of 2 vectors can be always broken up into a symmetric and a skew symmetric part. By the way, I found in the literature that Grossman actually put this together. It was one of the last things that he published, and the historians had dismissed his publication. But in fact, it was finally one of the last things that Grossman ever did was to actually combine the inner product and the outer product, and that's the thing that provides the foundation. Now, notice this wedge product. The product, it tells us that collinear vectors anticommute and orthogonal commute, and orthogonal vectors anti-commute. So that's the geometric interpretation in terms of algebraic terms. So, for example, let's take a couple of unit vectors on the unit circle, A times B, and the inner product is familiar to you, but notice the I here is an element of area, and not a vector as Hamilton originally called it. And now, if we combine those two, the inner and the outer product, you see the famous formula for e to the I theta for an angle. The concept of rotor, then, is take the geometric of, we can multiply, for 2 dimensions, it's equivalent to a complex number, and, well, you will be familiar with those representations. This is to show you how smoothly the use of complex variables and fit in to the geometric algebra. This representation of complex numbers is actually a special case of spinors, and it generalizes directly to n dimensions. Now just look at 3 dimensions, geometric algebra for Euclidean space. We can take an orthogonal frame of vectors, and I call them vectors sigma 1, sigma 2, sigma 3, because that equation, I equals sigma 1, sigma 2, sigma 3, occurs in many, many books on quantum mechanics. And these sigmas are regarded as Pauli spin matrices. However, the insights that, putting the insights that come from Clifford and the rest, we can recognize that in fact, whether or not these 3 vectors, which produce a volume that squares to -1. Okay, so here are the basic properties. The unit pseudoscalar, which is a unit element of volume for 3 dimensions, it squares to -1. It commutes with all vectors, and if you multiply the pseudoscalar times a vector, you get the dual, which is a bivector. The vector cross product is just using this duality. So that explains how the cross product is so special in 3 dimensions. And you'll notice that the notation here fits absolutely perfectly and consistently with the notation for vector calculus, which is in standard physics. The relationship to the geometric product, then, is that the outer product is the dual of the cross product. Now let me tell you a general theorem. Most everybody is here. Anybody that's familiar with Quaternions should be familiar with this theorem. But it requires understanding that U is a unit quaternion, where the dagger is actually the same dagger as Hermitian conjugation if we were using matrix representations, but this is, we're not using the matrix representation. So U is what is called a unit quaternion in the history of U. But X is a vector. Now, if you took the dual of it, then you would have a quaternion. Now, U is even. Now, you can just square that, and we get the following theorem that any rotation, or every rotation in 3 dimensions, can be expressed as the product of 2 reflections. And this generalizes to n dimensions in which we're no longer doing quaternions, we're using geometric algebra. This theorem applies, it is independent of signature, so every rotation can be expressed, actually any orthogonal transformation can be expressed in this canonical form and known as the Cartan-Dieudonné theorem, that every orthogonal transformation can be expressed as the product of reflections in hyperplanes in an n-dimensional surface. But that's equivalent to just generating the U as a product of n vectors. Now, the advantages of this form over matrix form for rotations, first of all, you'll notice it's completely coordinate free. The composition of rotations is utterly simple, and the parameterization, all parameterizations, I wrote a book on classical mechanics that does everything using this calculus, and it has the parameterizations. I have used it with NASA for space flight calculations and shown that it's more efficient. You might like to know that the engineers that have to do the complicated, the very big calculations for description of spaceflight control using quaternions, they found that quaternions are absolutely more simpler than using matrices. So now we can map the matrix representation into quaternions. I won't go through the details. It's pretty neat formula right here that is this thing called psi, which is 1 times the product of orthogonal vectors, generalizes and it gives us a direct, simple calculation that will move you from matrix representations to the coordinate-free geometric algebra formulas. It's invariably, however, to use rotors without without reference to matrices. Now this looks really nicely in orthogonal matrix. So we just imagine we have a frame of 3 vectors. It's generated by this rotor, which is a unit quaternion form. And the rotor equations of motion, it has always of this form, and that omega is a bivector, which is dual to a vector, and that is the rotational velocity from dynamics. And you can take a frame of vectors and rotate it, but it's completely determined by that omega. This rotor equation is easier to solve than vectors or 3 by 3 matrix representations. This is just a proof that the derivative, that the angular velocity has to be a bivector. Now it turns out, in a book, in an example, in my mechanics book, I have the application for magnetic resonance experiments, which are very important in physics. Unfortunately, you'll notice that the font is screwed up by Microsoft, by various switches, and so I won't go through the detail of that, but it is an extremely beautiful and useful and simple application for the description of magnetic resonance, which is used in describing how MRI machines work. That's the fundamental equation of what's going on. Now let me say a little bit about the origin of mathematics. The eminent Russian mathematician was an expatriate and taught at the Harvard of France, the École Normale Supérieure, for some 10 years after he escaped from the Soviet Union. And then he gave at the International Congress of Mathematicians in 1997, he gave a very long and remarkable talk on the teaching of mathematics. I'll just mention some of the things he said, including his first lines, which you might not agree with. Mathematics is a part of physics. Physics is an experimental science, a part of natural science. Mathematics is the part of physics where the experiments are cheap. In the middle of the 20th century, notice, middle of 20th century, that's the end of World War II. It was attempted to divide physics and mathematics. One way that it divided, the main way it divided is that before World War II, physics was a requirement, a minor in physics was a requirement of a math major, almost universally. But then, the consequences of this separation turned out to be catastrophic. Whole generations of mathematicians grew up without knowing half of their sciences, and of course, in total ignorance of other sciences. The current state is that physics is no longer a minor for math students, and I conclude that physics must be fully integrated into the math curriculum. We could spend a month just talking about this issue. This is a perspective which might be a biased perspective as a mathematical physicist, but I'm half mathematician and half physicist. Actually, 1/3 mathematician, 1/3 physicist, and 1/3 philosopher, which is a number of books of philosophy. So that makes me pretty bad in all three of them. Okay, now if you want to know more about this, here are two websites. This is the website that has my papers on it, and this other website is at Cambridge University for the Cavendish Laboratory, the astrophysics group, where geometry and algebra has been nurtured, and there are, I don't know, maybe 100 dissertations in using geometric algebra at Cambridge University. So I won't talk about the other references. They're easy to find. Once you find these websites, my website will give you can get either one. Okay. let me say something about universal geometric algebra. We imagine that we have a vector space of dimension n, and a signature r plus s is equal to n, generates a real geometric algebra with this product, an inner product and an outer product. This has a fundamental formula, which you might recognize that formula just before this actually is a generalization that includes the Laplace expansion for determinants. Okay? It's just dotting one vector into a whole lot of other vectors. So this is just the fundamental issues of universal geometric algebra, and that covers a huge amount of mathematics as a mathematical system. It does not have any imaginary numbers, but you can do anything that you do with matrix algebra in this way. And it can all be done in a coordinate-free form, and in particular as geometric algebra, geometric interpretation. This slide gives you a kind of picture of a n-dimensional geometric algebra as scalars, vectors, 1 vectors, 2 vectors, 3 vectors, up to n vectors, and which are pseudoscalars, and that'll look at n dimensions. Okay, now this is just the algebra part. The next part, which is important, now somebody will have to give me some time. How much time is got? How much should I have? 15, 10 minutes?
15 minutes.
Okay, so I want to get just a little flavor of geometric calculus, the idea of directed integrals. We have a multi-vector function, a multi-vector is a thing that is a combination of vectors, bivectors, trivectors, the general thing. And so there's a calculus of these functions. The volume element on a manifold, and I will call these things vector manifolds. That's appropriate. Vector manifolds are unique and have uniquely excellent properties. So the directed measure actually, think of a plane. You've got an element of area which you're going to integrate. But the area has a directionality associated with that. So this is fully worked up, and a directed integral is here on the at the bottom, expressed as a volume element, which is an m vector, an m-dimensional volume element of some function of the manifold. The fundamental theorem of geometric calculus is this. Now, here is an issue. This del, which is, I'm using the symbol del sometimes because it has this operator, gives us also what you are familiar with in three-dimensional vector calculus. It's the same del that gives you the divergence and the curl. So there is only one vector operator. And that's something that is, I think, very much missed in mathematics and in applications, that there's only one kind of vector operator, and what you need what geometric algebra enables you to do is to make variables, vectors as variables. So this is the vector derivative on a manifold, and here is the fundamental theorem of calculus is for n-dimensional manifold, and also known as Stokes Theorem, but this is actually more general than the Stokes Theorem that is used in the calculus of differential forms. So I'm not, this is just, we don't have time to go through details. I just want to get you a kind of picture of these things. So the differential forms are generalized in geometric algebra. We have a vector valued k form is the element of area, and this thing, you'll notice the notation, like the exterior differential, actually hides something else in the mechanism, so that the fundamental theorem of calculus can be written in this form. And there are various special cases. Now, the derivative, so this is the vector derivative, and I'm using the particular symbol, the partial, is because that's the vector derivative projected onto a manifold. And Cauchy's theorem and Cauchy's integral formula, which you know from complex variable theory, actually applies to any dimensions using this algebra. And so the advantages of the vector derivative is that it applies to all dimensions, it's coordinate free, it simplifies the fundamental theorem of calculus, and generalizes the division. And it has an inverse operator. This inverse operator has been rediscovered in special cases in many mathematics journals. The Cauchy integral formula, the Cauchy integral formula is generalized to, in complex variable, what you need to generalize it is to have not only line integrals, but area integrals, and that has been generalized and can be put in this form. Now, this vector derivative is commonly called the Dirac operator. It is the same vector derivative, the same to differentiate with respect to a vector. That's the whole point in geometric calculus, is how do you differentiate things, differentiate vectors and vector fields and all of those. Now, in the famous Dirac algebra, Dirac operator is actually just the vector derivative. Here it is written with respect to the gamma vectors, which is just a frame of orthogonal frame in 4 dimensions. This del, which is the Dirac operator, is the derivative with respect to a space-time point. And that gives you, we have divergence and curl, and the fundamental theorem of calculus versus the Stokes theorem. These are put together. And so essentially the vector derivative is that you have the integral on the surface of an area divided by the volume, and then you shrink it, and that will give the general. Now, there's an areolar derivative and a volumetric derivative. These are in the mathematics literature, in the Quaternion literature, but in fact, there's only one general derivative. If you have the sufficient. Now, Cartan's differential forms in geometric calculus, I'll just notate a couple of things, and the whole theory of differential forms is included. And this is in my book, Clifford Algebra to Geometric Calculus. So this is the end, or if you will, a beginning. And I hope it gives you some thoughts about how you can improve and integrate mathematics in such a way that it will be integrate fully with physics. And so every mathematician can be a physicist. Thank you.
Anybody have any questions?
Yeah.
So, I'm pretty sure I can do pretty much everything you've just said you can do with your Clifford algebra using standard differential forms and the Hodge dual.
Yeah, except their scalar value. Standard differential form. That last slide that I showed, which is actually the basic calculations for differential formula were there, except the geometric calculus allows it to have multi-vector values, whereas
Well, they're differential form values, right? They're not scalar values, they're tensor values. And and that generalizes to, I am not shackled to flat space if I use differential forms and Hodge theory. So what's the advantage to using?
well, you can translate it into these ways. Now, the advantage. What I've actually I've actually said that you can make the transformation from differential forms to the others. So I don't want to make a unique judgment on that.
Okay.
Okay.
Okay. Any other questions before we go to our next speaker? Okay, let's give a hand for Dr. from Arizona to talk to us today, and I'm really, really glad to have had the privilege to have you in our talk. Okay.